quantum theory, as you know, actually, if you treat it seriously, radically changes our view of what reality may be. It's difficult to cling to a sort of traditional nuts and bolts view of reality if you've been sufficiently exposed to quantum theory.
The world is not as it seems. Behind the apparent solidity of everyday objects lies a seething shadow world of potentiality. So begins the book Quantum Reality by Jonathan Allday. That's in the preface. And I have to say that I've got a number of books on quantum mechanics, probably well over 100 by now. And I have to say that this is one which I come back to time and time again. It's one of my favorite books on quantum mechanics, probably because it's simply presented, it's easy to understand, and it doesn't duck any of the difficult ideas or issues there. Jonathan Allday is quite a prolific author. He's written a number of other books too. He's just written, more recently, Space-Time, an introduction to Einstein's theory of gravity. He's also done a book on quarks, leptons, and the Big Bang, and also Apollo in perspective. And of course, this one that we're looking at today, quantum reality. So it's my great pleasure to welcome Jonathan to our podcast today. Thanks for coming, Jonathan.
Well, thank you very much for inviting me, and thank you for that extremely flattering sort of approval of the book. I'm glad
actually meant it as well, because it is the one I keep going back to. Let me begin by asking you a more basic question about, can you tell us something about yourself? How did you come to be the author of so many books on physics, theoretical physics, or quantum theory, general relativity, fundamental particles? How does that all come about?
Well, I've always wanted to, writing has always been a sort of an ambition from when I was a child. And it, in a way, although I'm extremely pleased to have managed to produce the books that I have, I'm also slightly disappointed that the great science fiction novel continues to elude me because I just haven't got any good ideas. So I sort of think of myself as a semi-failed writer, in that my ambition to be the next Isaac Asimov has just been absolutely doomed. But on the other hand, I have managed to produce, as you said, some books that have been well received, and that's got to be good enough for everybody.
So, coming back to the quantum reality book, which I say is I find a very well expressed book, very clearly laid out. And what kind of market were you aiming at? Who was that directed towards, and why did you feel it needed to be written when there's such a plethora of books around on quantum mechanics? Was there some niche we were looking for?
The niche I was looking for was, I didn't think there were many books around which actually dealt with the interpretation as well as the mathematics.
Oh.
I wanted to do a book which gave a decent enough grounding in the mathematics. You're not going to be able to go away from reading quantum reality and sort of do solve university level questions, that sort of thing. That wasn't its intention, was never to be a textbook. Its intention was to lay out the mathematical apparatus well enough for people to understand where quantum theory was coming from, and then to tackle the interpretation, the philosophical side of it. That's why the sort of subtitle is Theory and Philosophy, because I didn't think those two things have been brought together in one book, at least not at the level I was aiming for.
The mathematics you've got in there, which is, you don't shy away from the mathematics, but you've expressed it in such a way, I would say, that probably you only need some school level, A-level mathematics to be able to understand what you've got in there, yeah?
Well, that was the deliberate intent, and I'm glad that you think it's worked. It was the deliberate intent was so that an interested, albeit one would have to accept probably talented, sixth form student could tackle it, and or someone that had done perhaps physics or a science degree many years ago and had wanted a refresh, or indeed someone who was perhaps hadn't done a science degree but a technical degree who wanted to mug up a little bit on quantum theory as well. And a sort of side adjunct to that is, it's partly that I don't think the quantum theory, as you know, actually, if you treat it seriously, radically changes our view of what reality may be. It's difficult to cling to a sort of traditional nuts and bolts view of reality if you've been sufficiently exposed to quantum theory. And I don't think that's seeped into the general populace sufficiently. I'm not suggesting that this book it radically changes that in the minds of most people, but its aim was to try and tackle that for at least a segment of an audience, to say, look, if we're going to take quantum theory seriously, there are some profound implications here about what we mean by reality.
Well, that leads me very naturally on to the next question. I think let's move into the realm of looking at quantum theory itself. Richard Feynman is well known for saying that those people who claim to understand quantum theory don't really understand it at all.
Yeah.
So what is the difficulty then with quantum mechanics? What's the key point which makes it so hard?
I think the key point that makes it so hard is that initially, at least, you're tempted to approach it as if it was a modified form of classical physics, rather than being, you know, actually you've got to hang up almost everything you know and start again here. This is radically different. So even if we use phrases like momentum and position and that sort of thing, which carry over from classical mechanics, in the context of quantum mechanics, they adopt a rather different meaning, or at least they give rise to questions about what you mean by them. And the danger is that you drag too much with you, which leads to confusions. As I said, you've got to hang it up and start again, really. When in my more mischievous moods, I sometimes think that if you could possibly tackle it, you'd teach quantum mechanics first and then teach classical mechanics as a limiting instance of that, you know, which would be educationally impossible, but actually ontologically probably a more valid approach. A little bit like teaching Lagrangian mechanics first and then saying, oh, look, Newton mechanics is a limiting case of this. You wouldn't ever approach teaching physics that way, but it's got an aspect of appeal to it.
So let me push you on this. What is the fundamental mystery, though? What is the anti-intuitive bit?
Yeah.
Is there something which you can focus in on and say, this encapsulates it? This is where it all changes and where you've got to change your picture.
Well, I think it is. I think it's the amplitude and it's the wave function, isn't it? I mean, it is this, whatever this is, this new thing that is introduced by quantum mechanics, the amplitude, which is all your fundamental calculations are based on figuring out what the amplitude for this is in this particular context, which you then complex square in order to get your probability out of it.
Can you tell us more about what this amplitude and wave function is? Because there may be some people who don't really know what that refers to.
Yeah, no, absolutely. When you in classical physics, if you're talking about the state of something, the state of this coffee mug, if you're going to be grandiose about it, this coffee mug is described by a collection of variables like mass, volume, the velocity at which it happens to be traveling, which relative to me is 0, thankfully, at the moment. And you have a collection of variables which have specific values at a particular time, and that defines the state of the system. Now, when you're dealing with a quantum mechanical state, you very rapidly discover that in certain contexts at least, that luxury doesn't exist, that there are well-defined experimental scenarios, which if you're going to try and explain what is happening within them, it would appear that the particle, for sake of argument, or the photon of light, is occupying what would appear to be multiple classical states at the same time. So one of the classic examples of this is a simple interferometry experiment where you have what's known as a half-silvered mirror. You fire a beam of light, a stream of photons at it. They split. Half of them are reflected, half of them are transmitted. You go through some more gubbins and then you recombine them again at the end. Now, in a standard wave interpretation of light, you would explain this by an interference effect. The waves go through a different path to get to the recombination point, slightly different distance. They started off in phase, they end up slightly out of phase, so they constructively or destructively interfere with one another. And if you want a wave interpretation of light, you can follow that argument through. When you're dealing with a stream of photons, that becomes a little more difficult to maintain that view. And when you do an experiment and you turn the wick down on your laser or whatever you're using, so there's only ever one photon traversing the apparatus at any one time, and you get a little ping your detector saying, yeah, the photon arrived. But after time, you still build up an interference pattern as if it were a wave, even though at any one time there's only ever one photon traversing the experiment. Then you start to sort of grapple with the idea that in some sense, the photon is creating its own interference pattern. You know, the photon is interfering with a different aspect of itself. And so whereas you think of a photon in some sense as a particle, it's got, again, classically, it would just have a discrete position, discrete velocity, etc. When it reaches this mirror, it seems in some sense to be going in both directions at once. So the individual aspects of the photon can recombine again to give rise to this interference, building up over a period of time, single photon by single photon. Well, what are these different aspects of the photon? And in a sense, that's what we refer to as the amplitude. It's this apparent layer underneath what we can classically observe, where you can combine amplitudes, you can calculate amplitudes, and they determine what's going to happen. But in some curious sense, they are not themselves directly observable. So that when the photon arrives at the half-silvered mirror, there is an amplitude for it to be reflected, and there is an amplitude for it to be transmitted. We would calculate the value of that, the amplitude to be reflected, the amplitude to be transmitted. But in order to get the interference at the other end, we need to deal with both amplitudes at the same time, which is in some shadowy sense telling us that something to do with the electron is traversing both paths, the photon is traversing both paths at once, even though classically that would be, you can't have a particle in two places at once.
I mean, the way you're using the word amplitude here, it's almost like the probability that something would go one way and there's some probability would go the other way, but it's not a probability on its own, is it? And that's the important thing about the amplitude. The amplitude is not a kind of a classical probability because it can suffer from this superposition principle, where the probabilities don't in the same way. So can you tell us something about superposition, if that's what's behind this?
Well, that's partly what I was alluding to in the idea of in this simple idea, when you have this, as I said, mirror that allows half of the light to be reflected and half of the light to be transmitted, which again, you know, if you fire a visible laser beam, you'll see both beams coming out and it's just clearly visible. But if you're dealing with a single photon and you're getting still an interference effect, then something which is not a probability is happening. And we know it can't be a probability because the probability would be that the photon 50% of the time goes that way and 50% of the time goes this way. So an individual photon on that classical approach would either go like that or it would go like that. In which case, when you look at the result at the other end of the experiment, you wouldn't see any sort of interference experiment. So that's why I use the phrase underlying. There's this underlying amplitude which comes forth when you actually have a situation whereby you allow the photon to explore both possibilities. The underlying amplitude does that, but you can't actually observe the amplitude. You have to calculate the probability from it.
So would you go so far as to say that quantum theory is classical physics plus superposition, or is it any more than that?
I think it's very much more than that. I think there is always a temptation to think of it as just being classical physics plus superposition. And I actually didn't explain what was meant by superposition. So let me just backtrack.
Yeah.
Superposition being this idea that at least in the realm of amplitudes, that a system that we would expect classically to be either here, there, or wherever appears to be able to occupy at the amplitude level all of these possibilities at once. So that when we are dealing with the evolution of a quantum state, we have to superpose or sum up all the different amplitudes for all the different possibilities. And it is that having to write the quantum state as the sum over its possibilities, which is in essence the principle of superposition. And that's what makes it radically different from classical physics. In some curious way we don't understand, the classical physics arises from this. But the danger is that you try to drag too much classical physics in at the quantum level, and that leads to not really understanding how quantum theory works, I don't think.
Well, let me ask this then, if we're talking about this interface between classical and quantum. You've spoken about a particle, which can be in a superposition of states, small electrons, something we can't even see.
Yeah.
What about if you magnify that up and turn that into a full-sized classical kind of object? Do they have a superposition of states? And do I have a superposition of states? Do you?
Well, this is one of the real profound mysteries of quantum mechanics is, you know, clearly we are all composed of objects which have quantum behavior, electrons, atoms, etc. have quantum behavior, yet in some way it's some cutoff point, whether it's a sharp cutoff point or a fading demarcation line, we get to the situation whereby you and I will exit this room through a doorway at the end of this conversation, would be profoundly disturbed if we were to diffract our way through it. Exciting though that might be for a short period of time. So we don't see quantum effects at some level, and yet we do see them at this level.
Sorry, I was going to say, I think I'm one of the only people who worries about when I walk through a line of bollards. For that very reason, where am I going to end up? It always crosses my mind, but I don't know why. But there we are. That's just.
I think that's what makes a physicist with a slightly philosophical bent.
But coming back to this macro object thing, does it tie in? I mean, this is where we come up with Schrodinger's cat, don't we? And the application of that. Can you tell us something about that and how that ties in?
I will, but sorry again, may I just backpedal?
Sorry, go ahead. I interrupted you. Yeah, go ahead.
No. I mean, keep me on the straight and narrow by all means. But again, this is something I need to bring myself more up to date on because of the second edition. But Anton Zeilinger and his group have been working on this demarcation line, and he's been doing some amazing work. Last I heard, he certainly had buckyballs, you know, carbon-60 molecules, showing wave effects, and I think there's a hydrocarbon. I can't remember which exact hydrocarbon it was, but certainly a larger molecule than a buckyball. He's got to demonstrate wave effects now, and I thought at one point, although this is a slightly contentious thing to be saying right now this second, I thought at one point his unspoken or sort of quietly spoken aim was to see if he could get up to the scale of viruses and see if he could demonstrate quantum effects at the virus level.
Well, to steal a phrase from someone in Apollo, it's a small step from a buckyball to a cat, isn't it?
No, it's a huge step. Yeah.
Huge step. Yeah, tell us why.
Yeah, well, just again because of the macro size. I mean, let's be clear. The idea of Schrodinger's cat was a, you know, as in Einstein's famous Gedanken or thought experiment scenario, was to actually try and demonstrate the fundamental strangeness of quantum theory by leading to an apparently absurd endpoint from a well-established quantum starting point. So the story goes that you have this cat, this poor cat is imprisoned in a box. I have some suitable boxes from my house move lying around the place. And you have a radioactive element in there. And during a period of time, quantum mechanics will be the underlying physics, which determines whether or not this radioactive element undergoes a decay. and you have some sort of detector inside the box as well, which traditionally is attached to some vial of poison. So if the system undergoes decay during that time, the poison is released and the poor cat suffers the consequences. Well, if you're going to describe the evolution of the atom using quantum mechanics, then you have a superposition of states. You have a superposition of the state that the atom has decayed and the atom has not decayed. And that is how you describe the evolution of the state up until the moment at which it actually does decay, this random moment at which the superposition of states collapses into the one instantiation. Well, to develop that further, then, the detector lies in the superposition of states, which has detected the radioactive decay or it hasn't, which means then that the vial of poison is in a superposition of states, which is that it has been cracked or it hasn't. These states being entangled in a sense with one another. And then, of course, that means that the cat itself, poor Moggy, is in a superposition of states where it is both alive and dead, which is, in many people's eyes, the absurd end point. And yet, from a mathematical stroke quantum description, that each step is, in a sense, inevitable, that you've been led from a perfectly rigorous, mathematically defined superposition of states, which defines your radioactive particle, right the way through to this poor old Moggy. And then you could take it further, because, the person who lifts the box lid to see whether the cat is still with us or not, until the point at which the box has actually been lifted, they could almost be in a superposition of states of having observed the cat to be dead or not. And then you bring in what's known as Wigner's friend, who is the chap that asks the person who observed the cat whether or not and it just keeps on going on and on and on. And that, in a sense, is the profound difficulty, I think, which lies with quantum cosmology. Our colleagues who are trying to write down wave functions of the universe, that the whole thing is part of an entangled, completely wave, what at the end causes it to collapse. Because wherein is the moment at which something or someone actually breaks the paradox and says, right, this one instance has happened, and then the whole thing shuffles its way back down again. And that's what leads to, I think, the many worlds interpretation being so popular amongst quantum cosmologists. Which
we'll come on to that in a moment. Let me just ask you, though, your own personal view of the Schrödinger cat thing. I mean, the standard person who doesn't know about quantum mechanics would say, well, it's obvious the cat is either dead or alive, and it can't be both at the same time. And yet the quantum physicist will say, well, the mathematics tells me it's in a superposition of states here. So, but you can't reconcile those two. If you look in the box, then you'll then collapse the wave function, and you either see a live cat or a dead cat. It's one or the other. But what's really going on? What does Jonathan Allday think is really going on there? Is there a superposition of alive and dead, or is that just a mathematical fiction that we have to work with? How do you view it?
I don't think there's a superposition of alive and dead. I do think there is a point at which a sort of region at which quantum mechanics will fade into classical, into a more classical regime. I think myself, my own personal view is that quantum mechanics is incomplete, that we are awaiting some new addition to the theory, which allows us to deal with this particular situation. Now, what sort of a new addition are we talking about? Well, at the risk of getting, not wanting to get too technical and go too far off conversation, people do talk about a hidden variable type theory, which is an idea that there's some underlying business below the quantum mechanics, which if we only knew and understood it, would allow us to make complete calculations and not have to rely on probabilities, which is another difference in quantum mechanics compared to classical mechanics. We do have to deal in probabilities in classical mechanics, often when the thing is too complicated for us to completely calculate. But in quantum theory, it's an underlying randomness that seems to lead to probabilities. So I'm not talking about that sort of addition. Roger Penrose has come up with this idea whereby if you sort of fold gravitation into it as well, in some which we don't yet have a proper theory of quantum mechanics and gravity, that actually the melding of the two will lead to an actual objective, what he refers to as the objective state reduction. In other words, he believes, as indeed I think I do, that this collapse, this breaking of the superposition, this multiple possibilities apparently going on at the amplitude level at once, resolves itself into one. I think there is some physical mechanism that leads to that. It's a mechanism that we don't understand at the moment. But my gut feeling, for what it's worth, is that there is some as yet unknown physical mechanism that leads to that. Penrose, I think, talks in terms of an evolving situation, and when it gets to be too, in a crude phrase, gravitationally distinct, then it will flip into one or the other. Bringing gravity into it in a way that's not fully clearly defined. But if you have, in a sense, if you have the photon going two ways at once, it's having a gravitational influence on its surroundings, albeit a very tiny one. But if you start to take those sorts of interactions into account, I think his developing theory is that at some scale, as this evolves, it will be forced to collapse into one or the other. So I'm attracted by that sort of an idea.
I think there have been people who are looking for ways in which to naturally trigger the collapse of the wave function out of its superposition of states, out of its position of live cat and dead cat, into one state, so that it happens automatically. But there are those people, of course, who don't believe that the wave function collapses at all. And you already hinted at that, so the many worlds theory. Could you tell us something about that one too?
That for me is a very interesting one, because I think I confessed it at one point in Quantum Reality, that I approached writing the chapter about the many worlds interpretation, thinking, this is a bit far-fetched, guys. But actually, in the course of researching it and writing the chapter, found actually there are many attractions to it. I mean, just to circle back, the fundamental problem we're talking about, as we both mentioned, is that if you do have a quantum system in this curious superposition of different possibilities, we seem to be protected from observing that. Something causes that to collapse, is the phrase, collapse into one state or another. We don't know how or why that comes about. And curiously, quantum mechanics itself doesn't describe it. The mathematics completely describes how a quantum state should evolve over time. But at some point, I don't know if you've ever seen that wonderful cartoon. I think it might be a Gary Larson or some Far Side cartoon, where two professors are scribbling on this board, and there's a comment in the middle, and then a miracle happens. And that's sort of what's going on. Quantum mechanics completely describes how this superposition of states will evolve over time. The mathematics is completely rigorous and, dare I say, elegant. But at some point, the miracle happens and the superposition collapses into one, which is not described by the quantum mechanics at all. There's no mathematics that says this is how it works. It just happens. And so the sort of the germ of the idea of the many worlds interpretation was that if the quantum mechanics mathematics doesn't actually describe state collapse, then maybe state collapse doesn't actually happen at all. In which case, how is it that we only see one outcome happening? Well, the answer would be then that we only see one outcome happening because we only occupy one branch of reality. That in fact, reality is multiply branched, and that the superposition of states is in a sense spanning multiple realities. And that when we see one particular instance coming about, we are following the line of one of those realities, but there is a parallel you and me having a similar conversation, but possibly with a slightly different color bookcase behind you, or slightly different leather armchairs, just different branches of reality in which all the different quantum states are being explored separately. So this superposition spans and evolves over all the different ones. And so the collapse never actually happens. One instance is in our reality, another instance is in a parallel reality, another instance is in a parallel reality. And one's tempted to say, as long as the infinity stones are holding it all together, then we're good to go.
The only difficulty with that, of course, is it seems an incredibly profligate theory, doesn't it? It seems to multiply universes almost to infinity, because every single decision that you make, which could have gone one way or another, it produces a new universe for you. And I think the average person in the street would say, well, that's just utterly crazy, fantastic, and nonsense. How could anyone possibly even believe it?
I know. I mean, that's the sort of approach that I took, you know, when I was first researching the chapter, that there was too much of an ontological price to pay, this multiple branching realities, for what seemed to be not much of a payback. Because I think there are alternatives, like we've discussed, some actual other mechanism involved, albeit that we don't understand it yet, which actually brings about the collapse for real. But having said that, you know, you've got to deal with what you've got. And I know there's a lot of very good work, well, who am I to judge, but I know there's a lot of profound work going on in quantum cosmology, attempting to tackle, you know, the evolution and creation of the universe in a quantum domain, where it's the only game in town. You know, if you're trying to write down the wave function or the amplitude for the whole universe, there is no person looking into the box to actually trigger that collapse to happen. You know, how do you trigger a collapse of a wave function into a particular universe that we happen to have without branching outside of the universe? So that seems to be a natural fit for the quantum cosmologists, that they don't have to worry about state collapse, because the you know, each different possible universe is evolving along its own branch of reality. A slightly more awkward question, I think, is not just simply, you know, the point and giggle as a philosophical refuted by I refute your argument, sir, by giggling at it, which I think is a little bit valid for the many worlds interpretation. The other problem is, you know, the continuity of our experience. You know, if, as you said, every decision that you and I make, it branches off into a different reality, what does that mean in terms of the continuity of who we actually are? And I think that one of the unsold or underused, maybe neither than the exact phrase, but, you know, when we're dealing with physics, I think we do have to remember our common sense experience. Often physics, you know, branches out very, very differently to our common sense experience, and we need to accept that. But we do have common sense experiences of the continuity of ourself and that sort of thing. And I think they need to be taken seriously as a measure of how well we understand the physics.
I mean, that does have implications, that many worlds theory, because in many of those decisions that we might make, we might not actually exist at all. We might have walked under a bus by mistake, and that's the end of us. But in another world, we didn't walk under the bus, and we still continue. And that's, again, makes it even more definedly distinct as a theory as to what's really going on here. Can we really believe that kind of thing happening? But there are
also parallel attraction to it. I mean, you know, it does open up if this were true, it would open up the possibility, albeit still extreme, you know, that time travel might be a possibility, because one of the ways in which you refute the notion of time travel is that the standard saw about you go back in time and murder your own father, therefore you were never born, so you couldn't go back in time to do it, etc., etc. Well, if time travel, because of quantum uncertainty or whatever, meant that you didn't go back in time in your own reality, but you went back in time into the parallel reality, you would then be murdering a parent that just didn't happen to be your own biological parent. And that might mean that, you know, which is an interesting thing to explore from a theoretical point
raises
of view.
Multiple complexities as well as multiple worlds, I would think.
It's not a serious argument for accepting the many worlds theory. It just means it opens up a domain for the theorists to play in. Right. And I'm always keen to keep them quiet.
What about some of the other interpretations? There are more prosaic ones than that one. I mean, going all the way back to Niels Bohr and
Yeah.
the way in which he had his famous Copenhagen interpretation. The idea, if I understand it correctly, is that we shouldn't even bother. If we don't look in the box, we can't say anything about it. We don't know whether the cat is dead or alive. And what we should therefore do is say nothing and not even ask the question about it, because it's not relevant to us or to the mathematics at all. And it's a bit like Wittgenstein's idea that what we cannot speak of, we should pass over in silence.
Yeah.
The idea that say nothing about it because the theory says nothing. Does that not have some merit to it?
I think it has more merit than possibly modern day quantum theorists give it. I think the attraction of a lot of Bohr's work, and I think, you know, it would pay some people to go back and read some of Bohr's original writings, in particular, without, again, branching off into a different thing, but his paper on the EPR paradox is a wonderful piece of work, I think. But
Tell us a bit about the EPR paradox, because that's quite an important thing about the entanglement, which some people have heard about. And it was Einstein, of course, who wrote the first paper on it with Einstein, Podolsky, and Rosen, and they presented some idea trying to refute Bohr. But how did that come about?
Well, yeah, I mean, the idea originally of the EPR paper was to actually show that quantum mechanics was a limited, was in some fundamental sense limited. And the paper started out by putting some very tight constraints on what was meant in the context of the paper by a physical variable. And then they explored the notion of having a system where there were two particles that were then separated. And if you took a series of measurements on this particle over here, they would actually, because of the quantum connection between the two of them, actually influence what was going on that particle over there. And this is this notion of entanglement. I mean, crudely, if the particles have this property called spin, they can either be spin up or spin down. And if the original state was spin 0, that meant that if this particle was measured and found to be spin up, then this guy was forced to be spin down, and vice versa. And according to their quite tight definitions of what meant to be physical variables, which were reasonably common sense ones, this would seem to defy what was meant by a physical variable, that you couldn't influence this guy over here without making a measurement on this guy over here, that something very odd, Einstein referred to it as spooky action at a distance. And in particular, if these were, as indeed I think Schrdinger's group has done, if these particular measurements were separated by quite large spans of space, that the effect on this particle over here could apparently be instantaneous, or at least faster than information could travel between the two at the speed of light, which, you know, for Einstein was a profoundly upsetting thing. Well, Bohr approached it from a radically different way, which was to say that once these two particles had interacted with one another, in a sense, you could no longer think of them as two particles. They were, from a quantum mechanical description, a single two-particle state. And that therefore you weren't, in a sense, communicating between two things. It was actually the properties of the whole state was what was going on. That if you measured this particle here, it would have an influence on that particle there, not because there were two particles, but because they were one quantum object together. And that was a sort of...
It's a radical way of thinking about the world then, isn't it? This jointness.
That sort of brings in part of what we mean by this radically different view of the world that quantum theory brings about. Because if the process of two particles interacting with one another causes an entanglement by which you can no longer really regard them as being separate objects, they've become a sort of melded quantum entity, then, you know, potentially all particles undergo an interaction at some point. And so potentially we're all, to some extent, entangled away with each other. Although entanglement is a delicate thing that can be broken if the particle interacts with or the two particle system interacts with something else. But it was Bohr's whole sort of philosophical approach in a way that I still find quite attractive in his way to try and cut through to the nonsense and get to the basics of it, and not be afraid of saying that quantum mechanics here is something radically different from what we know from classical mechanics. But if I could just say one more thing. Sorry.
Go ahead.
The other aspect of the Copenhagen interpretation, I think, is that they drew a hard line between the quantum world and the classical world, and that it was a sort of presumption of their theory that the classical world existed, because it was the eventual interaction between the quantum realm and the classical realm that gave rise to the state collapse. That's when it happened. That there was the acceptance that, you know, you could describe an atom in a quantum way, and that in principle you would go higher and higher and higher and bring things more and more and more under the same quantum explanation. But at some point you had to draw the line and say, from this point onwards, things are classical. Without that, the theory didn't make sense. And that was the Copenhagen interpretation, or an aspect of it. At some point you had to draw the classical line. The problem nowadays is that we don't know where to draw the classical line. And indeed, it doesn't seem to be a hard line. If it is, it seems to be more of a gradation from one into the other. And so I think people these days are much more are dissatisfied with the Copenhagen interpretation, because it doesn't tell you where to draw the line. It just sort of dogmatically says there must be a line somewhere. And so for that reason, it doesn't get the serious treatment. But I think there are other aspects to it, like we've talked about, which are worth going back and looking at again, even though I tend to agree this dogmatic hard line is a limitation of the interpretation.
Are there any other interpretations of quantum mechanics which you think are worth considering or looking at?
I think all the interpretations have to be worth considering. I mean, this is one of the curious things about quantum theory, is that the mathematics doesn't constrain the interpretation. Again, why is it different to classical physics? In a sense, it isn't. It's just exposed us to an issue that was already there in a more radical way. If I come back to my coffee mug, you know, we describe it in physical terms, in terms of variables like mass, velocity, and everything else. And they have mathematical symbols and can be manipulated mathematically in classical mechanics. And we tend to not think it's a problem, because it's natural to associate v, our velocity variable, with the velocity of the mug. And you develop the ideas with momentum. Momentum is not quite as visible, but there, and energy. I mean, yeah, okay, energy has got a pretty obvious classical interpretation. What is that we mean by energy? Well, okay, we've got an idea what we mean by that. But in quantum mechanics, when you're faced with the amplitude, this thing that we've been discussing so much, which you can't directly observe, and we don't know what to make of it. So in that sense, we're exposed to things that make perfect sense and can be manipulated perfectly mathematically, but we're not sure how to make the link to reality. We're not sure where in that link lies, if indeed there is a link between the amplitude directly and reality. And I think what I'm trying to say is that the link, that jump of making the link between the mathematics and the reality, was always present in classical theory. It was just slightly more obvious what you should do. But in quantum mechanics, it's not at all obvious what you should do. And so therefore, every interpretation has to be worth looking at, because the mathematics doesn't constrain what the interpretation should be. The interpretation is, in a sense, a free domain.
Yeah.
And so this is where, in a sense, you branch out into philosophy, because the physics isn't, in a sense, or at least the physics at the mathematical level, isn't constraining the interpretation, isn't constraining the philosophy. And so then you start to ask questions about, well, okay, which interpretation makes sense from the philosophical approach that you're most comfortable taking? And I think, again, that was one of the things that I found fascinating about the founding fathers, people like Heisenberg and Dirac and Bohr, is they were well educated from a philosophical point of view, and they weren't afraid, at least if the records of their conversations are at all accurate, in tackling the philosophical issues while they were banging their heads against the physical theory.
Do you think that, looking ahead into the future, I mean, some of these interpretations are somewhat mutually exclusive. They can't all be right. Do you think we'll be able to distinguish between them as we go forward? Will there be some way where it'll be shown that the Copenhagen theory or interpretation is wrong and many worlds is right, or vice versa? Is there something which could do that, or will we be forever at the mercy of an interpretation here?
Well, the simple answer is, I don't know. Sometimes I don't know. Is the
I do ask you difficult questions here on the.
Yeah, well, I would hope that is the case. I would hope that I would live to see it, but one lives in doubt. My gut feeling, for what it's worth, again, is that some point, perhaps a la Penrose, in a more well-established merging of gravity and quantum mechanics, we will see something that gives rise to a mechanism for state collapse, a physical mechanism for state collapse. And that would rule out the many worlds interpretation, for example, or at least put it on a footing whereby it wasn't required anymore.
And also rule out the Copenhagen interpretation, because there would be something which would lie below the surface, which could tell us something else, like when it collapses or why it collapses.
Well, it may not give us a definitive moment at which it collapsed. It may not remove the absolute probability level from the quantum mechanics, but it might mitigate it in some curious way.
Don't you think the search would go on if it didn't? That people would say, well, I'm not happy with that. I want a more definitive answer. We got a classical frame of mind. This is where you came in, I suppose. We need to think radically different. But doesn't the classical frame of mind say we must have certain answers to these problems? We must have certainty. And yet it may well be that at the end of the day, that's forever going to elude us. Is that a possibility?
I think it is. I really do think it is. I think the randomness inherent in quantum mechanics, I believe, is something that's here to, it is a profound level of reality, and it's here to stay. If you're going to press me a little bit further on what my own feelings about as concerned, I don't often confess this because it is slightly off the wall, but I think we actually need to take the amplitude a little bit more seriously as something which has an objective reality. Not the sort of reality that we are used to at our classical level, but I tend to think of reality as being layered. There's another phrase, I can't remember the name of the physicist who coined it now, but veiled reality, that we're looking down through a veil into the quantum level.
Are you talking, when you say take the amplitude more seriously, are you talking about something like the Bohm interpretation, which literally does take the amplitude very seriously, isn't it?
Something along those lines, yes, something more along those lines. And there are attractions to Bohm's interpretation, and if we want to sort of delve into that, there's this allied notion, which is not at all well developed as far as I'm understanding, called active information, whereby information theory might actually come into physics, or information might come into the world, and in some sense the information about the entire context of an experiment may actually influence what's going on within the experiment, in terms of defining what quantum states are possible and how the quantum states evolve, that context of the whole experimental apparatus. So I think there is possibly something to be explored along those lines.
The difficulty with those kind of things, and indeed Bohm's idea, is of course that it comes back again to your first point, that the reality is very different from what we expect. That would involve non-locality being built into the system. I mean, the quantum potential is a non-local field, and if you were to try to explain it in terms of in the way which you've just described, that there'd be non-locality built into a system like that, and that would change the picture of the universe. Yeah, sorry.
Yeah, no, I think that's an important intuition. I think that non-locality is well enough demonstrated by the increasingly sophisticated experiments on entanglement that we can actually expect reality fundamentally to be a non-local affair, and that what we observe in our everyday reality is a limiting case of that. When the sort of the quantum fades into the background, we get this emerging. You see, it's the reverse, isn't it? That we should stop thinking about quantum theory as something that's classical. The classical world has somehow emerged out of quantum theory. It's a slightly ridiculous, picturesque phrase. Imagine plucking something out of a vat of water, which is then dripping back into the vat. You sort of pull classical theory or classical world out of the underlying quantum mechanics in some strange way. And there may well be clinging bits of it left even at the classical world. And that seems to be, you know, this line at which the demarcation happens is more of a gradation. I mean, you know, people never expected, I don't think, I don't know how, certainly 10, 15 years ago, that quantum effects may be significant at the biological level, but there's an emerging field of quantum biology where they are seeing quantum superposition, quantum type states actually becoming significant in biological systems.
Sounds like we might get back to Schrodinger's cat again by a different route.
Well, that would be a slight embarrassment, I think, if that were to be the case. And you certainly wouldn't have a cats queuing up to take part in the experiment, I'm sure.
Probably not. Jonathan, now we're coming to the end of our time, I'm afraid. Can I just ask you one last question? Because your book, Quantum Reality, I believe, is undergoing a second edition review at the moment. Can you tell us something about what you plan to enhance the book with? What else are you putting into it?
I'd like to get, I'm intending to get a chapter on quantum computing in. I think that's a big emerging field. I mean, one of the ideas behind writing the book in the first case was I was conscious that there was a sort of growing quantum hype around the place, that quantum mystery was being used increasingly as an explanation, almost like you say, crop circles, oh aliens, or oh quantum mechanics explains that. And I wanted to try and give at least some general readers an idea of what quantum mechanics was about, so they could make judgments when people started to say, oh yes, we can explain this because it's all a quantum world, etc., whether that was a valid use of it. And again, quantum computing is emerging as a field, and we're talking about it more and more, and it creeps into sort of news articles and popular press. Let's have a look at what's underlying that and try and separate out what may be the quantum hype from the reality a little bit. And then to sort of the section I'm proudest of in the book is the tackling of quantum field theory. I don't know whether other people would view it as successful, but I was most pleased with that chapter of the book because it's not something that's often tackled, I don't think, at that level. It was tackled in a slightly different way, not unique to me. I piggybacked on the ideas of others. And to me, it gives a nicely accessible way into quantum field theory. And I wanted
certainly a lot easier than Borkin and Drell, I should think.
Well, we've all been through the Borking and Drells.
Quite a tricky thing.
It's idea of trying to take identical particles seriously, in a sense that leads you into quantum field theory, because I think it's got important things to tell us about ontology as well, or at least important questions to raise about ontology that over and above just even normal quantum mechanics. When you get to quantum field theory, a slightly broader domain opens up. And so I wanted to push that a little bit further and see how far we could get into talking a little bit about quantum gravity and quantum cosmology. While at the same time, trying to address what is probably the fundamental shortcoming of the book, which is it's very long, and try and compress it down a little bit at the same time. They might be two aspects of uncertainty principle. You know, you can either have a longer book with less things in it, or a shorter book with more. I don't know whether the two are in fact mutually compatible, but that's what I'm going to try and do.
Well, as you began your book, the world is not what it seems, and it seems to me that we've covered some of those areas today. So the world certainly isn't what it seems. But Jonathan Allday, thank you very much indeed for your time today, and thank you for a very interesting conversation.
I've really enjoyed myself. Thank you very much indeed.
Take care.